Today we're going to discuss iRVision for precision assembly applications. This is a very, very valuable use of robotics and machine vision. Last week, Mr. Chris Blanchette talked about robotics and some of the overview of what FANUC offers for those folks doing automation and assembly applications, integrating robotics and machine vision for precision assembly applications. And my task here today is to talk to you more about some of the key technology issues, going into depth in some of the technology that we're going to address when we try to use robotics machine vision for precision assembly. As always, I won't have time to cover every single topic, and I hope that you'll follow up with questions if you have any regarding how to specifically execute some of the things I'm talking about. And I hope that all of you go back to your plants, to your applications, with just a little bit more information, maybe just one small snippet of information that's going to help you make your next application more successful. So let's get started. I'm going to start out with an overview and a review. An overview of assembly and a kind of a review of machine vision and what precision is. Let's start by talking about assembly. What are the characteristics of a robotic assembly application? Well, as I thought about it more deeply, I realized that really robotic assembly is mostly concerned with part placement, whereas a lot of our applications are concerned with picking a part and getting that part out of somewhere, and then we're maybe less concerned about how it gets placed. Certainly maybe still need precision with the placement, but in assembly, pretty much all of it's about part placement. We want to pick the part up accurately and be able to put that part onto another component, assemble that part in the grip onto another component, and perhaps attach it, solder it, bolt it, do something with that part that turns the other component, the secondary component, into a more complete assembly. And the bottom line when we talk about the issue of precision in automated assembly is that just by the nature of the applications, assembly may require higher accuracy with respect to the robot and the machine vision. It's an important thing to note here as we get into a discussion about robotic assembly, that machine vision in this particular application is a key enabler to automated assembly in a flexible environment. Think about that. We really can't do, we certainly can do an assembly where both the part that's to be picked and the part that's to be assembled are all hard fixtured, and all you have to do is blind pick the part and blindly put the part into the assembly. However, when we're talking about flexible automation and making a robotic precision assembly cell, machine vision plays an important role in turning that cell from just what it would be an extension of hard fixturing into a truly flexible cell where we can have the parts coming in a variety of locations or in possibly unknown locations or imprecise locations being picked and placed precisely into the assembly to complete or at least advance the assembly of that particular component. So machine vision is a crucial enabler to robotic assembly. FANUC has the robots to achieve this, and I am going to go into the technology here today of iRVision to help you achieve those functions as well. So bottom line, robotic assembly is really part of a flexible automation environment. Many assembly processes that are manual or accomplished with hard fixed automation can today be addressed with vision-enabled robot technology. And it's my belief that we as integrators and we as the manufacturer of the components are not fully realizing the possibilities in robotic assembly environments. And so I hope that between the presentation that we had last week, and please go online if you haven't seen that from Chris Blanchette, and my presentation today, that you'll start to consider more possibilities for including flexible automation and in assembly in your integration repertoire. Benefits of flexible assembly, of course, I think these go without saying. It produces a work cell that's easy to maintain, with potential for quick part changeover, multiple part processing. In the bottom line, it provide overall improvements in productivity and profitability. We get the response that sometimes the initial higher cost to design and create a truly flexible work cell might be there, but overall and in the long term, the marketplace says that flexibility is productivity and profitability. Requirements for a flexible work environment and integrating a flexible work cell. First of all, diligent upfront application analysis, applications and component specification, and cell design. I know that hard fixturing can be a very difficult and challenging design process, but to make that a truly flexible and robust work cell and flexible automation, I think requires even more diligent upfront analysis, specification, and design. And as I said before, iRVision is a key enabling technology. There are certainly plenty more, and again, Chris talked about those last webinar, but iRVision is really the key enabling technology to make flexible automation a reality for your assembly project. So let's talk about the word precision. I felt we needed to have a quick review about this term. When we talk about precision assembly, that's not by any means an engineering use of that term precision. I want to give us this quick overview of where the word precision resides in our engineering vocabulary. The two key words as we think about an engineered system in robotics and machine vision are precision and accuracy. Precision is the concept of being able to be repeatable and reliable over a long run and over a large statistical sample set of your processing. Accuracy is quite more basically a term that relates to how accurate your system is able to reproduce a specific result. Precision can be independent of a specific result, whereas accuracy requires us to reproduce a specific result. Now, how does this affect guidance applications? Well, we'll talk about in a moment the issues of precision and accuracy with respect to the robot and how iRVision or machine vision inspection affects that. But let me ask you the question: precise, accurate, or both? Let's look at this. I do this a little bit tongue-in-cheek. I don't know how many of you are golfers, but if I were able to, on a long par 3, hit that green, and for my golf game, if I were even able to hit it on a repeatable basis, I would have to say that I'm pretty precise. That means that I'm able. I don't know exactly where I'm getting it, but I'm able to get that golf ball onto that green in a repeatable basis within that global target. Let's look at this, however. If I were able to get the golf ball that close to the hole, we might say that that shot was accurate. But does that make my golf game accurate? Not necessarily. If I were able to do that time after time after time, that means I have an accurate system. Both a precise and accurate system in this case. But we noted from the first picture that we can be precise without necessarily being accurate. Let's go forward with some of those terms, just again as a very quick review. In quality and in metrology and in even guidance location, we have a variety of terms that we use and sometimes use them incorrectly. Here's a list of some of the common terms, but let's look at 4 of those that impact us as we think about robotic precision and machine vision. First of all, resolution. Resolution is the smallest increment of measurement in our system. If it's a machine vision system, the smallest increment of measurement might be dictated as a pixel or the real-world representation of a pixel. Uncertainty is the measurement error. We don't see this a lot, but it's the ratio of precision to the tolerance band that's being reproduced. Precision, as I said earlier, is the degree of reproducibility. Not necessarily the actual point that we're guiding the robot to or the point at which the machine vision system can find an object in space, but how reliable or reproducible our function is. If I can find the object in the machine vision in the iRVision process at the same position time after time after time, that indicates a precision or a high degree of reproducibility. Now, is it accurate, however? Look at our chart to the right there. The true value of the object that we're locating might be, or the object that we're placing using the robot, might be slightly different from the center of the values that we're finding within our band of precision. That doesn't mean we're not precise. That means we're not accurate within the real world, but sometimes that's not a critical metric. However, when we talk about applications that use random guidance, particularly like the guidance provided by iRVision, accuracy can be the critical metric. That means that in a random environment, in a random world, part being in unknown positions, we need to find that part not only precisely, in other words, when it's in the center of the field of view, not just report that it's a certain position in the center of the field of view. We need to consistently report that that is an accurate world position in the center of field of view. So accuracy can be a critical metric. It's not always a critical metric in robotic guidance or in robotic applications, but in random guidance using machine vision, accuracy it can be the critical metric. Here's the key, and here's the gotcha. Robotic precision is very well known, and as Chris pointed out last week, the FANUC robots are highly precise and even more precise than some of our specifications, some of the specifications show, because our specifications are in some different, our precision values are specified in some different metrics from some of the competition. So if we see precision metrics from FANUC, we can very well assume that they are even better than some of the equivalent numbers being stated by other manufacturers. However, accuracy is way much harder to quantify. The accuracy of a robot is whether or not where that robot goes when it's moved to a commanded world location and not just a trained point. Precision or repeatability, reproducibility is when we train a point and the robot goes back to that point extremely well every time. But where is that point in the world? If we move the robot to a commanded world location, such as might be provided by iRVision, that accuracy, while it may be very suitable for our application, that accuracy is just simply harder to quantify. So I wanted to compare these two terms and make sure that you understand, this may be a review for some of you, but make sure that you understand that these two terms are not equivalent and that they have different meanings depending on the type of application we're executing. It's important here to talk just for a second about error stack-up. Stack-up error is the contribution of all the components in the process to the overall error. A lot of times we might concentrate only on the error produced by the vision process. And in fact, some people mistakenly say, well, if the vision process can find this to a certain reproducibility or to a certain accuracy, then we should be able to pick and place that part to that reproducibility or that accuracy. And I think you can see that that's not always the case. There's always stack-up error. It goes from the robot, as you see my pictures here to the right, it goes from the robot to the gripping mechanism. Of course, the camera is involved, and even to the extent, depending on your application, it may even go to the extent of the accuracy and reliability of your taught user frames. So as you go into a precision application from a technology point of view, let's make sure that we always identify the processes, the components that might contribute to this error stack-up over the broad scope of the application. Okay? Moving right along, let's talk about achieving better precision and accuracy for our application. And I have four general categories of technology that I'd like to either introduce you to or at least review for you that may help achieve better precision and accuracy in your iRVision application for precision assembly. Let's start with IR calibration. Again, something that was talked about in last week's presentation, which, by the way, will be available online on the FANUC Integrator website, along with all of the other FANUC Friday webinars that have taken place. The many great webinars that have taken place over the last many months. Just as a review, IR Calibration is a suite of semi-automated utilities to perform robot mastering using an iRVision camera. Let me clarify that IR Calibration is not part of iRVision. It's a separate option, a separate suite of utilities. It does use an iRVision camera, but that camera does not have to be enabled through iRVision. And in fact, for some of the functions, that can be a camera that's just temporarily mounted for the purpose of doing IR calibration. It provides number one, utilities for robot mastering, but also provides utilities for automated, or at least a semi-automated, tool center point and U-frame setting. Very valuable for precision applications. And I should note that these functions, at least the functions of automated tool center point and U-frame setting, are also available in iRVision utilities if you only have iRVision and do not have the IR calibration option. So why do we talk about remastering and these automated functions? First of all, all robots do lose mastering, at least to a very small extent, in a variety of ways. One of the ones we hate to see is a crash of the robot. Certainly can in some way affect its mastering. Even shipping the robot can possibly affect the preciseness of the mastering of the joints. The automated process, again, IR calibration, I've only pointed out a few of these routines, but the automated process of vision mastering automatically uses a target grid to master J2, 3, 4, and 5, and uses the iRVision camera to provide that mastering function. The results are, in many cases, significant. We do see improvements in the precision and also in the accuracy of robot pick and place using iRVision when we use precision mastering and remastering through the IR calibration suite. Let's mention, though, for a moment, the idea of automated TCP and U-frame setting. I know all of you have used manual methods in the past to manipulate and create a TCP or a U-frame, and TCP, and then use that TCP to manually touch up a U-frame. When we talk about improving our precision, improving iRVision capabilities, particularly when it comes to the calibration step, the better we can do with defining the tool center point and the U-frame, as particularly the calibration grid frame, the better our iRVision precision will be. And as I said earlier, just the frame itself can be a contributor to the precision and accuracy of the system itself. So these automated tool center point functions and U-frame functions not only are convenient and much more easy to use than manual touch-up, they absolutely do technologically improve the results of your application by getting at a very highly accurate tool center point, highly accurate U-frame. Just a quick graphic of how these things come together. The vision mastering uses a visual target, which is actually a specific calibration grid, not a specific calibration grid, but one of our iRVision calibration grids. And the camera looks at that grid, moves around the grid, and discovers mastering corrections for the robot joints. TCP setting uses an external camera to look at a target on the tooling that will become the very accurate tool center point discovered by the vision operation. And then we also have the frame setting using multiple targets on a frame with the camera robot mounted to discover the U-frame of that particular object. As I pointed out, I'm sorry, let me move on to very briefly calibration. I'm going to get back to what I pointed out about these functions being available in iRVision. They'll be on the next slide. In iRVision calibration, if you've, as a review, and if you've done this before, you'll know that we use a touched-up grid to create a relationship between the world coordinates in pixel space and the world coordinates in the robot world space. iRVision calibration, is necessary, and the accurate calibration is critical to precision assembly applications. The purpose of the calibration is not just to map world coordinates, but also to correct for planar and perspective image distortion. All lenses have a certain amount of perspective image distortion, and of course, inconsistencies in the mounting of the camera over the plane of the part introduce planar distortion. Good quality calibration, well-executed calibration, accurately corrects for all of those errors within the lensing and within the imaging, within the scene of the imaging. We have a couple of different types of calibration available, and I'm going to just touch upon these, but I'll end up by telling you what we need for precision assembly applications. First of all, orthogonal calibration is the simplest of the iRVision calibration processes. It calibrates a single plane. It does not consider height variation. That means that if the part changes height, the calibration will become invalid. The calibration doesn't take into account lens focal length, nor does it take into account the possibility of the part varying in height. So when you do this calibration, the calibration frame, the calibration grid has to be at the height of the work piece or the object that you're going to pick or the object that you're going to locate if it is a robot-mounted camera. And only the features at that plane are reliable when the object's found. If the object is above or below that plane, we can say that those points are perhaps inaccurate or at least indeterminate at that point. But let's talk about perspective. Perspective is a calibration when we're looking at precision applications that even if you don't have consistent part variation in height, perspective calibration has the potential and usually does produce a much more accurate, much more precise location of the object in space. Perspective calibration takes into account lens configuration, either by direct entry of the lens focal length into the iRVision process, or by using a two-plane calibration. You can accomplish this either by moving the robot or by moving the grid frame in front of the camera. So it's an absolute necessity if you have parts that are possibly not going to be at the same Z height, the same very accurate Z height all the time. And just as a quick explanation, we see a couple of planes and a camera here. The height between those planes changes. If we've calibrated at plane 1, as we can see in this image, and then a part is presented to us, or an object is presented to us with its surface in plane 2, if the camera has not been calibrated in perspective, the camera will report that P2 point as if it were on P1, even though the XY relationship of that part in the field of view is not the same because it's at a higher image plane. Because of the angle of the field of view, the part will be perceived to be at a different position. With perspective calibration and knowing what Z height that part's at, we're able to correctly provide the position of that part when it is in P2, even though the calibration was done in plane 1. So that's perspective calibration. First strong hint, first strong tip about precision assembly applications: use a perspective calibration when at all possible. It will improve the accuracy of the points returned for the application. Okay, I did promise that I'd talk briefly about a couple of automated processes that are similar to the IR calibration processes and are included in iRVision. First one is automated grid frame setting. It sets a user frame from a calibration grid automatically. There are only a few parameters to set, and whether it's a robot-mounted camera or a fixed-mounted camera, the robot or the grid moves in front of the camera and discovers where that grid is in space. Of course, if it's a robot-mounted camera, it delivers a U frame. If it's a fixed camera and a robot-mounted grid, it delivers a tool frame. But in either case, the results are much more accurate than what you can do with your eyes and even careful jogging of the robot for manual grid frame setting. You can use this even if you don't have if it's a fixed grid on a fixed location, and you don't have a robot-mounted camera. You could temporarily put a camera, an iRVision camera, on the robot. Even an external USB camera that's available with iRVision that can be hooked up to the teach pendant, and use that to do a very accurate automated grid frame setting. Again, if you haven't tried it, something for you to look into for any precision application, particularly one involving assembly. Another one that's another automated process that's available in iRVision and provides some of the similar features that the IR calibration functions that we talked about do, is robot-generated grid calibration. This is a semi-automated process. If you haven't seen this before, very easy to use, very easy to implement. Not fully automated, but semi-automated, and it performs a very accurate calibration from start to finish using the robot to manipulate a target. It's only good for a fixed camera, but we have a lot of situations in assembly where at least one of the cameras is fixed, depending of course on the application. It's very beneficial if you have large fields, but we find that you can use this in all cases where space permits, and there are suitable parameters to allow you to constrain the moves to a certain extent, and other special ways we can make this function work in smaller spaces. As I said, it's only for fixed mount. And finally, it creates a calibration program that can be reused without operator training. Just a TP program that executes on the teach pendant. And a side issue is, as promised, it does deliver a tool center point. It delivers the TCP of the target, just like the IR calibration TCP, automated TCP setting would deliver in that package. Bottom line is, that's calibration in a nutshell, and the bottom line is, I encourage you to, especially for precision applications and what we're talking about in assembly, to consider these automated processes. They will improve the results. They will make your life easier in terms of execution, but they will improve the results of the calibration process. Okay? Next step, what do we do? How do we squeeze a little more precision out of our iRVision application? One good starting place always for any iRVision application is lighting and imaging. Most experts in the machine vision field say that lighting and imaging contribute more to the accuracy and reliability of a vision application than anything else. Some people say it's more than 90% of the success of an application, and with iRVision, that's true as with any machine vision application. Number one, always use dedicated lighting for iRVision. By dedicated lighting, I mean suitable lighting that covers the field of view in an acceptable way to eliminate glare, eliminate shadows, highlight the features that are key to reliable location. As you certainly don't want to highlight background, but you certainly want to highlight the important features on the parts, and that sometimes requires very creative lighting. I would like to see you use dedicated lighting that overcomes random ambient plant floor illumination. And there are a variety of ways to do that. Another webinar has discussed a lot of lighting techniques, and I just want to review and remind you that lighting is that important. And finally, a good lighting technique and good dedicated lighting technique is repeatable for all part types, variations, and presentations. This is one of the big critical things that comes into play in an assembly application. Of course, in order to implement flexible automation, we're trying to pick parts that are in unknown orientations. We don't know where the part is. We don't know where it is in the field of view, and sometimes it changes a little bit even in its pose or in its orientation. Lighting is the key to making that successful over all variations and all presentations. So test well, design well, and implement well when it comes to lighting for not just precision automation, but even precision assembly, but even all iRVision applications. Some lighting techniques that I find to be kind of useful in assembly. This is by no means a broad rule, but in my years of doing probably literally hundreds of applications in assembly, one of the big tools that I found useful in lighting for this type of a precision application is backlighting. Backlighting creates a silhouette of the object and allows you to eliminate background confusion, to singulate parts more easily, and to use very discrete edges, even for the sake of error proofing along with the location process. We sometimes use diffuse front lighting. By diffuse front lighting, I mean soft lighting that covers the entire field of view to eliminate specular reflection or glare from the objects and from the background that would confuse the location of the objects and cause imprecision and inaccuracy in our location tools. And then finally, spotlighting. We overlook some of the specialty lighting components sometimes, and with assembly tasks, particularly on the place side, when I need to find the object or find the opening, the object, the thing that the part and grip has to go into, sometimes highlighting just the area of interest with spotlighting improves my results at that end. Now, I by no means have given you a complete discussion of lighting. Again, that's covered in another webinar, but the point is, consider the possibilities of a variety of lighting. Don't just use a single lighting source, and find something that works specifically for application. The challenge is, as always, consistent features, as I said, over a variety of part types, part presentations, and of course, the strong contrast that we need between the foreground and the background when we're locating the part. With that, let's move on to imaging. I want to talk for just a second about camera resolution. One of the biggest topics that comes up when we talk about iRVision and when I get questions about iRVision is that of camera resolution. And what is the right resolution for my application? Now, we're talking about precision applications, precision guidance for assembly in this specific application. And so what I'd like to point out is that doesn't necessarily immediately, as soon as we say the word precision, say the word accuracy, that doesn't necessarily immediately suggest that we have to have higher or ultra-high camera resolution. It may in your particular application. I want to point out the realities of resolution as we consider the issues of precision and accuracy. First of all, the thing that enables this is we have powerful algorithms. Not just FANUC. Of course, FANUC has wonderful, powerful algorithms, but certainly machine vision, the world of machine vision has extremely powerful algorithms to locate, find, and test objects that are within the field of view. And let me start with something really simple. When I talk about resolution, I like to go in this direction. We look at the circle over on the far left. Think for a second. I'm only going to give you 2 seconds to answer this question, but how many points do you need to define that circle? 3 points. Correct. I think you all got that one right. We only need 3 points to define that circle, but what happens if I have one of those points that, because of inadequate resolution, one of those points is slightly off of the actual observed edge of the circle? The result is going to be that I have a really bad locate on that circle. It's not going to accurately locate the centroid of that circle. The good news for us is that all of our algorithms that are designed to do location Things like geometric pattern matching, blob location, compound locator tools, all use many, many points around the circumference of the circle to discover the circle. In math, if you remember your high school math, that's called an overdetermined equation. And what happens is there are so many points that are discovered around the edge of that object that small errors introduced by lower resolution, small errors in the individual point will not dramatically affect the absolute center or the absolute origin that's returned by the algorithm. And that's why for most location applications, going to the extent, the cost, the speed reduction, and so on of super high resolution imaging is not necessary. If we look at that image in the middle there, I have some spades, some electrical spades that we've located with geometric pattern matching. And you can imagine, even though it doesn't show around the edges there, you can imagine that the edges of those spades are all included in the location result. And what happens is that even if we miss a few of those edges, or even if a few of those edges are slightly out of place due to the resolution of the camera, the returned origin of those objects is going to be highly accurate and highly repeatable, because it's an overdetermined equation using perhaps hundreds, if not thousands, of edges. In the converse, let's look at the image to the upper right. Let's say I want to find that part in a scene where there are a lot of similar parts, and that part only makes up a very small. I don't show the whole view here, but that part only makes up a small part of the scene. Now, one might say from my previous statement that yeah, we've got a whole bunch of edges in that part, and we should be able to use lower resolution to find that part. Where does that fall short in this case? Well, the bottom line is that those edges are very narrow edges, very small edges. They're not large gradient transitions. And so it may be the case, and I can't say for every individual application, but it may be the case that this application, not because we're still not using an overdetermined equation, but that this particular part, this particular image, may need more resolution just because we need to get a certain number of edges on a feature, those little small features in that on that part. We need to get enough edges on that feature to actually extract a reasonable gradient to deliver the matching of the geometric pattern match or the edge location or whatever we're using. So, bottom line, my point is, make sure you're using the right resolution, but don't exceed the necessities of your application just because we hear the word precision assembly. We can do some very wonderful things with reasonable resolution on any application. Okay? So how does this get implemented? Well, the thing that affects our resolution is, of course, the size of the sensor that we're using, but where that gets delivered is through the lens. The field of view and the resolution are all manipulated by the lens. The lens selection dictates the field of view, and then by relationship, the field of view dictates the spatial resolution. By spatial resolution, I mean how many millimeters per pixel I'm able to get in the image. And where a lot of people get confused is that the field of view is simply a relationship between the camera standoff and the lens focal length. A question I get is, can I move my camera away, farther away, to get it out of reach of the robot and still keep the same field of view with this lens? What's the answer? No, you can't. Camera standoff and lens focal length create field of view, and those three are mathematically joined. If you move your camera farther away to get the same field of view, you have to change the lens focal length, and so on with all three of those parameters. I show a little tongue-in-cheek view of all of the calculations that are involved in working with a standard commercial lens. But if you want to make this easier on yourself as an integration partner, we do have a new lens and image properties calculator that is a small, very compact PC program loaded on your PC, and it will do all of these calculations and many more for you automatically. So if you don't have that, contact the ASI group or contact me directly. We can make sure that you get your hands on that very easy to use calculator. But that's the story about lenses and how they create resolution through the field of view. One final hint when it comes to imaging with respect to camera resolution, lenses, optics, and so on. In many cases, particularly for this type of an application where high precision is required, or any application where we need high precision out of iRVision, I recommend that you use the longest focal length lens possible to get the narrowest possible image angle. Why? Let's take a look at this just simple box or cube. It could be a box, it could be a small cube in our field of view. And look at what happens when I image that in the center with a camera using a low focal length lens, in other words, what we call a wide angle lens, and you can see the angle of the lens. Look at what happens when that part's imaged in that using that type of a lens. The field of view actually sees the top edge of the far side of the image and the lower edge of the near side of the object, producing an image much like we'd see at the bottom, where you see the dotted white line. That represents the top of the box to the right, but to the left, we're seeing the bottom of, or the side of the box. It confuses location algorithms. And this is not, again, unique to iRVision. This is just Machine Vision 101. This happens with any type of image, whether you're able to rectify the image or not. A wide-angle lens produces this kind of an image that can and likely will confuse the reported centroid or the reported offset, center of offset of the origin, of the part being located. With a higher focal length lens, or a longer focal length lens, a higher numeric number in the focal length, that error in perspective of the resulting image is reduced, and we see less of the side of the object, more of the top of the object, and thereby reduce the perceived error in the production of the origin or the production of the centroid of that object. So when you can, get the camera further away, use a longer focal length lens, you'll get a better image for guidance in these types of applications. Very quick review. Best use of iRVision processes and tools, the actual tools that you might be working with. Of course, we have the 2D single view functions that use robot mounted camera, fixed mounted camera, and to find user frame offsets. That would be for the pick side of the process. And we also have fixed frame, fixed mounted camera with a part in grip that would be used to provide a fine-tuning tool offset once the part is in grip. We have multi-view processes to improve the accuracy of our find using either two cameras or multiple fields of view over smaller areas of view, so that we can find that object a little bit better without the error that might be introduced by a larger field of view. And I even want to throw in here a depalletizing vision process, because a depalletizing vision process can be used for things other than depalletizing. One of the key things the depalletizing process has going for it is that you can feed in the expected Z height of a part if desired, so you can use that process. Unlike something you can't do with a 2D single view, you can use the depalletizing process as a 2D guidance process, but you can change the Z height of the part as you go on the fly at runtime. So a couple things to keep in mind, just to review the processes that you have available in iRVision. Now let's talk about some command tools. Just again, by no means a complete discussion of iRVision command tools, but the ideas that might help you achieve higher precision for assembly type applications, and perhaps for all of your applications. First of all, a possible rule of thumb. Certainly, all of my rules don't apply in every situation, but let's consider this one of the possible rules of thumb. Work in shifted ROIs always for tighter location of features. A shifted ROI is a shifted region of interest is accomplished by using the iRVision window shift tool. We use a locator child tool underneath that shift tool to find the tool, to find the entire part in space, roughly finding that part, perhaps with lower accuracy expectations, lower precision expectations, but nonetheless to find the part and see how its position is changed. We then, all of the subsequent parent tools underneath the window shift tool will be floating relative to the position of that part in space. As you can see from the original part position on top, and then the floated regions of interest on the bottom. This allows us to constrain the subsequent processing within a smaller region of interest, avoid the possibilities of confusion as we're trying to find individual features that more accurately locate our object, and maybe allow us to use better parameterization within that smaller window, again, to achieve higher precision. So one quick hint: try to work in shifted regions of interest using the window shift tool to tighten up your inspection as you look at a part. Some more command tools that maybe you haven't had broad exposure to. First of all, blob location. Blob location is the concept of finding an object that has a contrast variance from its background, either white on black or black on white, based on a specified point of thresholding. Now, there are ways we can even make that an automated point of thresholding. But at a specific point of threshold, all the objects that are lighter than the threshold turn white. All the objects that are darker than the threshold turn dark. And as you can see in my example here, I'm using that to identify a specific object in the field of view, or identify multiple objects in the field of view. One of the great advantages of blob for the pick side is that you can have the blob find a part for pick without particularly knowing what the part is in advance. Certainly it's good as a locator tool and does a somewhat of a good job at differentiating parts, but in terms of if we just want to get the part off of the feeder, off of the conveyor, off of the in-feed device to pick it for subsequent processing and then a placement for an assembly process, blob might be a good candidate for you to use, in that it doesn't require at this side doesn't require you to know a lot about the part itself. Combination locator, another tool I find people don't have a lot of experience with, but a very powerful location tool. It uses multiple child tools to find the location of an object. Why could this be better for us? Well, even if we have a fairly small field of view, if we have an object that comprises a good portion of that field of view, one generic location of that object might introduce error, particularly if the object is not rigid, not completely rigid, might introduce an error if we use just one tool to try to find it. With a combination locator tool, we use multiple tools and then combine those geometrically to calculate the position of the object. In this case, I've used two line locator tools to find the center of the arm and the center of the leg of that hex wrench, and then combine them at the intersection to be the position calculation for that particular locate. Perhaps words of wisdom, review on command tools, something that might help your application in to achieve more precision for an assembly process. Edge pair locating. Edge pair locating is the concept of finding gradient, not grayscale edges, and by gradient we mean, of course, black to white, white to black contrasts between object and background. And find those edges in space and return the location of those edges, usually the center of a pair of edges. This is a pretty precise locating tool. It's not one of those tools that we call an overdetermined locating tool. It's a discrete locating tool. So where this might have particular use for you is after the part is already in grip. Let's say we've rough located the object using a blob, using GPM, using some other locator tool, and then we present the part in grip to a camera for a much finer, precise location of that part and apply a tool offset once the part's in grip. Sometimes this is critical to a precision assembly application. It's very difficult, as we'll learn in a moment, just even due to physical reasons, to get a part picked with high degree of accuracy, if not for the vision side, very often sometimes because of the physical side. Looking at that part once it's in grip using something like an edge pair locator or other locate tools is something that may be an absolute requirement for your application, and you should think about designing that in at the front end when you think about precision assembly. Finally, I won't go over this too much because I think most of you very frequently use the GPM locator. Again, a geometric pattern match tool, very powerful tool and very good for a broad scope of locating tasks. Okay. With that, let's conclude with just a couple of slides on hints and tips here for integration techniques in precision assembly applications. There's the agenda. Let's go right into that. First of all, design your automation, your part presentation to best enhance the process. Very often I see people go into the design phase of a assembly application or even other applications trying to revise a manual or a hard fixturing process to accommodate robotic guidance with machine vision. This is sometimes just not the most efficient way to do it, and sometimes introduces errors that are going to make your life harder in the long run. Consider the needs of the vision and robotic technology first at design time. Understand what that has to be, and then apply that to the existing process or to a whole brand new process as needs be. Gripping issues. The gripper is often the key component. I shouldn't say key component. I guess key component is a good term. iRVision being the key technology, let's call the gripper the key component. We know the robots are precise. We know the robots deliver the performance we want them to deliver. Where we have to really concentrate our efforts is in the iRVision as a technology, and I want to share with you the idea that the gripper is sometimes the key component. We like to grab parts with vacuums, and I have seen people attempt to do assembly applications using grippers that are just vacuum grippers. Here's the error when we talk, or here's the problem when we talk about this in terms of high precision, highly precise assembly applications. Vacuum grippers, by their nature, introduce error at the point of grip, particularly for light objects, particularly for smaller objects. We can show you high-speed video and other examples of how this happens. But what really does happen is that as a vacuum gripper approaches a small and somewhat light object, by the mere act of gripping that object and executing turning on the vacuum and gripping that object, it changes the target location of the object from what the vision system provided to a different location. So in other words, the part gets gripped at a different location than what we expected it to be gripped. So it's in the grip, it's reasonably accurate, but if we want true precision, what do we need to do next? We need to find out if the gripper grasped the part exactly where it was located by vision and exactly where we guided the robot to go pick it up. Often that's not the case. What do we do to overcome this? I mentioned it a bit earlier. We add another camera to look at that part once it's in grip, and this is the true secret of high precision. That is looking at the part once it's in grip, and also looking at the object maybe in some cases where the part has to be placed. So keep that in mind. Not only does the vacuum introduce errors, but certainly there are other possibilities where gripping techniques introduce the error, and I want you to consider that in your error stack up as you design and consider for assembly applications. Finally, the need for leverage when we're talking about gripping. Look at the image right in the center there. We have a 3-finger gripper, and that's perfectly fine. What if that 3-finger gripper, though, was able to, under force, allow the part to move a little bit? We'd no longer have control of that part, and we wouldn't be able to push that part onto the bearing that you see just below the large piece of metal that the three fingers are holding. In this case, where the design of that tooling has been correctly put together such that the tooling not only grips the part, but grips it in a way that it provides a positive force without changing the position of the part as it goes onto the bearing. This happens more often than you might think in an assembly application, and is, again, the source of some potential error as you design for your best precision in assembly. Okay. Finally, a couple of little rules here for iRVision, and I've suggested these. I've suggested a couple of these. First of all, we'll call it pick first, look later. That means do a rough find for the pick, get the part in grip, and then find the part correctly in the grip as it's being held. I don't need to say any more about that. Technically, what you'll be using is a fixed frame or a frame offset for the pick, and then apply a tool offset once that part is in grip and head it over to the placement position. And then the other one is look where you're going. If you have a fixture, if you have a component that you have to place the object into that may move slightly, even if it's fixtured, you may need to find that assembly target for placement. Use a robot-mounted camera or use a fixed camera if it's appropriate to find where the part's going, and use that as another fixed frame offset along with the tool offset for the part in grip to get the part accurately and precisely into its assembled component. And then one last word about finding the part in grip. Keep finding the part in grip. Another technique that's very successfully used is to continually find that part in the grip and correct for the position at the last move. In other words, look at the part as it moves at various stages, as it moves towards the placing position, and then as it gets to the point of no return, we might call it, look at it one last time and make a final correction. And then place it and make the final small move to place it into its receiving location. We might call this visual servoing, although it's not really real-time visual servoing, but properly executed, it has a similar effect and can, again, very significantly increase the placement accuracy in a precision assembly application.